Okay, so for this problem, we'll consider two bases of R2. V1 consisting of the vectors 1, 2, 3, 4, and a basis V2 consisting of the vectors 1, 1, and 1, negative 1. One of the questions that I've been asked to consider is how to change from coordinates in V1 to coordinates in V2. So I will start with the following, right? What does it mean to change? Well, actually to have a coordinate system. So let's start with this. Let x1, x2 be a vector in R2. Since V1 is a basis, right? We know that there are unique numbers A and B such that you may write x1, x2 as A times 1, 2 plus B times 3, 4. So this is nothing else but a linear combination of the vectors in the bases V1 and 2. And in this particular order, so you would say that the coordinate of this vector associated with this, the first coordinate of this vector associated with the basis V1 is A, and the second coordinate of the vector x1, x2 associated with the basis V1 is B. Well, but then you would say, this equation that we really have here is nothing else but something of the following kind. You may express this in the following setting: 1, 2, 3, 4 times AB, right? So once we have that at our disposal, we have equivalently the following equation. If I multiply on both sides by the inverse of this 2 by 2 matrix that I have here, I get the following. I have AB is equal to 1, 2, 3, 4 inverse times x1, x2. Oh, okay. So this is just a relation that goes back and forth. Nothing of a surprise, because as we expect, when we form a matrix from the columns of from the column vectors associated with the basis V1, well, we're supposed to expect, we're expecting to get an invertible matrix. Nothing of a surprise. But then I can just repeat the process with the second basis. Similarly, there are unique numbers C and D such that x1, x2, the vector, is equal to C times 1, 1 plus D times 1, negative 1. So as just we said, we will say that C is the first coordinate of the vector x1, x2 in the basis V2. And we would say that D is the second coordinate of the vector x1, x2 in the basis V2. Okay, but again, we're going to really rewrite this equation in matrix form. 1, 1 times CD. So once we have this available, I would say something along these lines. Well, CD is equal to 1, 1, 1, negative 1 as a matrix inverse times x1 and x2. So look, This is now what I'm going to incorporate. This is saying that I can obtain the coordinates CD by knowing the vector and computing an inverse. The same thing that I obtained for the vector x1 and x2, along with the inverse of the matrix 1, 3, 2, 4. But then look, if I were to make a combination, this is what I get. So CD is equal to 1, 1, 1, negative 1 inverse times 1, 3, 2, 4 times A, B. What does it mean for us? Well, we're effectively making a translation. We are saying that if we know the coordinates of a vector in one system, for example, in the system B, in the coordinate system associated with the basis B1, then it's possible to know the coordinates in the system associated with the basis B2. So this is what we call the change of coordinates matrix. From where to where? Well, from B1 to B2. Now, it's not a surprise that we may invert this relation and say, well, if you want to translate from B2 to B1, meaning to be able to express AB in terms of CD, we will simply invert the matrix that we're given here. So similarly, we would get 1, 3, 2, 4 inverse times 1, 1, 1, negative 1. What will be this? Well, the change of coordinates matrix from B2 to B1. Now, something to be remarked here is that these two matrices are inverse to each other. So, well, let me know in your comments if you'd like me to generalize this result and provide a full explanation with details in a higher dimensional case or in the general case. Okay, see ya, take care.